Example 13. An open box is to be made from a square piece of cardboard that measures 40 inches on each side. To construct the box, squares that measure X inches on each side are cut from each corner of the cardboard as shown in the figure. Express the volume V of the box as a function of X. Determine the domain of V. Now, this is a basic, let's make a box problem. And these are pretty commonly happening in pre-calculus and calculus textbooks. Okay? There's some more complicated let's make a box problems in your homework. More complicated than this. Boxes with lids and stuff and how we construct them and everything like that. Volume is, for a rectangular solid, volume is simply length times width times height. So to do part A, I simply want to determine the length, width, and height in terms of X in order to establish the volume of this box. Right? In order to establish the volume of the box, anytime you look at a picture in the two-dimensional picture here, I want you to look at this picture to establish what part of that picture represents the base of this box. So looking at this square in the center represents the base of the box, right? And then whatever's being cut out here is what's being folded up. That's going to represent the height of the box. So the base is going to be the length and width. The height's going to be the part that's folding up. So in some of these more elaborate pictures that you get in the book where you have, like, it's like got, I don't know, maybe something like this, and they got to cut it here, and they do that. Something like that, where this is the box, bottom, this is the top. This is folded over double to make it reinforced and stuff like that. And then this side folds up to make that side. You have a base and you have a height. All right? And length, width, height, that's what you're trying to find out. And there's always X's here. All these are X's here. And maybe this was some number to be given, let's say 60. Well, this is 60, and there's 3 X's, 4 X's being taken away from, right? And these are equal size, top and bottom, right? So 60 minus 4x divided by 2. So this would be 30 minus 2x. This would be 30 minus 2x. There's ways of finding out how big pieces are. Okay, so it's usually how big the cardboard was to begin with minus some x's. And in this case, since there's a top and a bottom, you got to divide by 2 because these are unknown and equal. So, you know, find out how big the whole piece is, divide by 2 to get what's left. So, I mean, that's the challenging part of these, if there's any challenging part at all. I don't believe it's challenging at all, but historically students have had trouble with these problems. So, that's one of my problems as a teacher is sometimes I don't find things challenging, the students find challenging, and there's a little disconnect there. So hopefully, based on historical evidence, that's sufficient. So, this is the base of the box. Three-dimensionally, we can see it there. They've even gone to the trouble of giving us the length, width, and height here already. But had they not done that, it says it's 40 inches on each side was the length of the triangle, or the rectangle they started off with. You're cutting X here, and an X here, and an X here, and an X here. You're cutting X by X squares off each side. So this is 40. 2 X's are being taken away, so this piece is 40 minus 2X. Same idea here. This is 40. You're taking X off each side, so 40 minus 2X is left for that there. And the height, of course, what we're folding up is X. All right, so length is 40 minus 2X. Width is 40 minus 2X. And height is X. So again, if I'm trying to find the volume of a rectangular box, that's how I do it. Find length, width, and height. Volume is simply the product of those 3 things as a function of X. So V of X equals length times width times height. What's left to do is to multiply that together. Notice 40 minus 2x times 40 minus 2x is just 40 minus 2x, the quantity squared, so we can shortcut that. V of X equals. So it's going to be 1600 minus 160x plus 4x squared, still being multiplied by x. Just square the first object, double the product of the 2 objects, or negative 80x makes negative 160x for foiling. Square the second, the squares are always positive. Next I'm going to distribute the x through. Another thing I like to do personally for this, I like to rearrange this. We usually get the numerical part first, up ascending order. I like to rearrange it so it's descending order. It's not required to be descending order, I just think it looks nicer. So I'm going to get 4x cubed minus 160x squared plus 1600x. That's how you do part A. Determine the length, width, and height of the rectangular solid, multiply them together completely algebraically. Okay. That's not the part that students tend to have so much difficulty with. The second part, the domain, is the part that messes people up. The domain of this function itself, polynomial function, would be all real numbers. Right? If it didn't have a geometric picture associated with it. Yeah. Right? The geometry of stuff is we can't have negative sides. Yeah. All right? So what I'm looking at here are three sides to a rectangular solid, and none of those sides can be negative. So the x's I pick have to create positive sides. They can't be zero either. A side of zero makes not a box. It's just a piece of cardboard, all right? So if I cut like 20 here and 20 here, I get 0 by 0, and I have like 4 squares of cardboard that are just not going to be much use to it. So what I want to look at here is each individual dimension. So to do part B, I'm going to do this in purple. All right? To do part B, I simply have to solve these three inequalities. All right? Now, in the case of this being a square piece of cardboard to begin with, the top two are going to get the exact same answer, and the bottom one will get you a different answer. Okay? You're looking for, in the end, you're going to get one greater than, one less than. That's going to give you your region. All right? Greater than this number, less than that number is between these two numbers. If you start off with a rectangle, you're going to get two different things here. It's going to be less than one number and less than another number. Take the smaller of the two numbers. So if it's less than 8 or less than 8 and less than 10, less than 8 is going to be the winner. All right, it's got to be both. All right, both less than 8 and less than 10. So if you pick 9, that's not less than 8. Then one side is going to be negative. So these two, the length and width, usually get you less thans. The height usually gets you greater than. All right, typically. So just know that if you get two different less thans, pick the smaller less than. That's the one that counts. So if I solve these, I'm just going to take one of the top two. 40 minus 2x is greater than 0, which means negative 2x is greater than negative 40, which means x must be less than 20. Keep in mind, we always want x to be positive over on this side. So divide by negative 2. Division by a negative requires flipping the inequality around. X greater than 0 is already solved. So as long as x is greater than 0 and less than 20, which in inequality world looks like this, 0 less than x less than 20. As long as x is between 0 and 20, we're going to get positive numbers in this. Let's try one. 19. 40 minus 38 is 2. 40 minus 38 is 2. 19 is 19. Everything's positive. It has a volume. If we try something that doesn't work in here, let's say 25. 40 minus 50 is negative 10. We have negative 10 sides. That's not possible. It doesn't make sense. All right? So that's my domain. And again, using good set builder notation, the domain is the set of all x such that x is between 0 and 20. All right, and real quick, again, just leading us into calculus, this volume, this piece of cardboard is what it is. I can cut out any size notch in the side that I want to create some box if I want to maximize the volume. All right, I know x has to be between 0 and 20. I want the volume to be the most it could possibly be. This graph I'm expecting to come up, hit a high point, and then go down. Wherever that high point happens is the magical x that we're looking for. So I go back to my calculator, put y equals, and I type in my equation, which was 4x cubed minus 1600x, or was it 160x squared plus 1600? X. All right, that was our volume formula, right? Now, I know that x has to be between 0 and 20, so I'm going to go window, x goes from 0 to 20, and let's go with a 2 scale for that. I don't know anything about y. Y is the volume of this box, right? I'm going to go 0, all right? And then I'm going to pick some big number, 1,000. There's no magical way to pick that big number. I'm just saying that's what I'm picking. And if I hit graph, if I can see the graph, you see it's not even on the screen. It went way up there. It's going to come down here somewhere, I hope. There it goes. Okay. All right. 1,000 definitely wasn't big enough, right? It looks like it wasn't even close to big enough. So let's go crazy big on this. Go 5,000. And let's go up by 500. I don't know. That should be pretty close.
Right there.
I say crazy big, and it was just big enough. Okay, all right.
Perfect.
So, right there is the maximum volume. It happens right here, 1, 2, 3, between 3 and 4 it looks like. All right. So, but again, I can calculate maximum. Calc, maximum. What's that?
Isn't an X and 2 scale?
Oh, yeah, 2, 4, 6, good job. So 2, 4, 6, 8, between 6 and 8 it looks like. So as far as the left bound is concerned, I know where my maximum is. I want my left bound left of that, so maybe pick something like 2 or 4. I'm going to go 2. Just make sure you're to the left of it. All right? The right bound, make sure you're to the right of it, so I'm going to go maybe 16. All right? So you can see my answer lies between these two boundaries. All right? It doesn't matter that this one's way off. I mean, it doesn't matter as long as you're on the screen. I couldn't pick 24 because I only wanted 20, right? Pick on the screen on either side of it. And then as far as the guess is concerned, as long as it's between 2 and 16, it's going to be a fine guess because there's only one maximum there. If it like went up and down, and you pick this wide range, that wouldn't be so good. But there's only one maximum there. Again, 2, 4, it looks like it's around 6 or 7. I'm going to guess 7. Hit enter. 6.666669. So about 6 2/3 would be the magical X that would make the maximum volume for this box. The volume would end up being about 4,740 cubic inches. All right, but again, that's the calculus part of it. This is the pre-calculus part of it. Creating an equation based on a property of mathematics, in this case the volume formula. Find the lengths of the sides to create a volume formula. Every side has to be positive to figure out the domain. That creates good math that allows us then, when we get to calculus, to re-investigate this problem, use some calculus to find out that magical X value, and then also use a calculator to verify our solution.